Okay, here's an information slide for the SoFiE Seminar Series. And here's a brief advertisement for the annual meeting of the Society for Financial Econometrics. It'll be next week. It was supposed to be in San Diego in person. It's been switched to virtual. Conditions are not quite yet there for us to do it in person. The good news is registration is free. And so you can do that using this information at the website link at the bottom of this slide. Okay, well, welcome everybody to today's SoFiE Seminar. I'm Andrew Patton, the organizer of the series. And today is a very special SoFiE Seminar for two reasons. Number one is I'm hosting Oliver Linton, the incoming president of the Society for Financial Econometrics. Oliver will take over the day after the annual meeting, which is so next weekend or something like that. Oliver will be our new president. And then the second reason is that this is the last SoFiE Seminar in this series, at least in its current sort of incarnation. So since this is the last one that I'll be hosting, I wanted to say a couple of words of thanks to different people who've been part of the series. So this is the 25th SoFiE Seminar. It's been going for a year plus a couple of days. We've had 55 different people speak or present or discuss or serve as panelists. We've had topics ranging from very applied to very theoretical, high frequency financial econometrics to low frequency macro finance and everything in between. And actually Oliver's paper today is in between the spectrum on both of those dimensions. We've had lots of different levels of seniority. We've had PhD students entering the job market for the first time, looking for their first academic job, all the way up to Nobel Prize winners and everything in between. And we've had lots of different countries and regions represented. And since this is a webinar, I think rather than country, most relevant is number of time zones. We're all stuck at home. We've had 8 different time zones represented in this seminar, from people eating breakfast. I'm just about to have lunch. Oliver and Andreas are about to have their dinner. We've had people from Asia and Australia waking up in the middle of the night to participate. So it's been really, really broad and really great in that regard. And I want to thank all of those speakers and panelists and discussants for participating. Second, I wanted to thank the SoFiE Seminar Scientific Committee. Nu Madahi and Ying Li serve on that committee with me, and they've been very helpful in finding great speakers and discussants for us to enjoy through this year. They also gave a lot of good advice when I was setting up this seminar about a year and a couple of months ago, getting this off the ground when we all first were learning how to work from our kitchens or living rooms or spare office. I also want to thank an informal member of that scientific committee, and that's Tim Bollisled, the outgoing president of the society. Tim is a neighbor of mine here in North Carolina, and he's helped me out a lot when I've hit a roadblock in an organizational aspect of the series. Third, I wanted to thank Matt Matisic. Matt is the technical whiz behind the SoFiE Seminar Series. He's an associate director at SoFiE, and he has been in charge of the email list that you may have received, the website. He's the official host of the Zoom meetings each week, and Matt has really made it very easy to run this series, and I really appreciated his help. So thank you very much, Matt. And then finally, I wanted to thank you all, the participants of this SoFiE Seminar Series. We wouldn't have a series without people turning up, either synchronously in this new language that we use live at the seminar, or asynchronous and watching the video later. I found these webinars, this one and the other ones that have popped up around the world, to be a good antidote to the claustrophobia of being stuck at home for a year or more. And I really enjoyed being able to engage with the research frontier and to connect with people in the research community. And we wouldn't have that without everyone attending and engaging with this seminar. So thank you for being a part of it. I really enjoyed hosting it. And I'm looking forward to seeing what's coming next. So this seminar will take a hiatus over the summer. And I understand that it may come back, or it will come back in the fall in some new format. So the website will reveal what that will be when it's finally figured out. I think with that, I'm going to now go into our final SoFiE seminar. So let me do the proper introduction of our speaker and discussant. Oliver Linton is our presenter for the day. Oliver is a professor at the University of Cambridge. His discussant is Andreas Neuhierl from Washington University in St. Louis. We'll follow the same format as the other 24 SoFiE seminars, 40 minutes for the speaker, 10 to 15 for the discussant, and 5 to 10 for Q&A. You can use the Q&A box at the bottom of your Zoom screen if you have a question. And if we run out of time, we'll continue the conversation in an informal hangout session after the main seminar. And with that, I'll turn it over to you, Oliver.
Okay, thanks. So hope you can all see this and hear me. So thanks very much to Andrew for kind introduction and for running the series for the last year and hosting so many great sessions. So let me just jump straight into the talk. So I should apologize that the paper and our work on this is really far from complete. We have a lot to do, and we understand some of the missing steps in the arguments and so on. So it is relatively preliminary. So I'm very interested to hear any comments that Andreas might have. So it is joint work with Greg Connor and Sharon Lee, so let me just get started. Okay. So let me just give the contribution in a nutshell. So we consider a conditional one-period monthly portfolio choice problem in a large N and large T setting with associated covariates, firm-specific characteristics, X, and time series predictors, Z or Z. So we assume a semi-parametric model specification, at least implicitly, in terms of both sets of variables. So that's going to help us to bring both of these variables into play. It's going to be a fairly simple portfolio problem. It's just one period maximizing CRRA utility function with known risk aversion. What we're going to do, though, is to proceed in two steps. So we're going to, first of all, find factor mimicking portfolios Q, J of them, through projected principal component analysis and a quadratic optimization to sort of select the right rotation. And then we're going to use those factor mimicking portfolios back in an optimization problem to find weights on those sub-portfolios through constrained optimization. So we apply our method to crisp stocks over the period 1967 to 2017, so 600 months and up to 2,900 stocks. We'll have, throughout, we will have J is equal to 3 tilting portfolios, and we will have a total of 33 characteristics to work with, and 4 time series predictors. So everything's going to be, as I said, semi-parametric, and we'll get into the details of that in a minute. Parts of what we do, we use a rolling window, and parts of what we do, we use the full sample. So I may not outline that at the correct time. So we evaluate in-sample and out-of-sample performance, and the portfolio, the performance depends clearly on the risk aversion parameter. We have a lot of work to improve the performance as we stand at the moment. Okay, so let me just start with the background here. So a classic portfolio choice problem. We have a risk-averse investor, concave utility function, maximizing expected utility with respect to portfolio weights W. If, as we know, so if U is quadratic utility, or we have Kara plus normality, we get the well-known Markowitz solution involving the following weights. So we have a closed form explicit solution. And I mean, this is probably still the most widely used method for portfolio choice with some bells and whistles. Okay, so it's still a very central model in defining portfolios. Modern work extends this to allow for the large number of assets case where we have particular problems because it's hard to invert the covariance matrix, and estimation issues play a big role in that. So some classic contributions of Ledoux and Wolff to impose a shrinkage on the covariance matrix to make it more regular, allowing you to calculate the inverse in an accurate way. Other approach is not to estimate at all, so use just equal weighting. So this has been in the literature, background literature. Of course, it does beg the question which N assets to select in the first place, but that's quite a large literature around this contribution. What we're working with really are factor models, and so that literature in this portfolio setting is also quite old. So Hammer and French and developed some of this, and it's nicely reviewed in Greg's book with Karachik and Goldberg, 2010. In the large dimensional setting, so this allows a dimensionality reduction by imposing a structure on the covariance matrix. This was extended in a couple of papers by Faniao and Mincheva, where they allow for what they call conditional sparsity, that is sparsity in the a dominant factor model plus sparsity in the idiosyncratic error covariance matrix. There's also some work trying to use high frequency data, which would allow us to improve estimation of the covariance matrix, but would not help us as far as the mu is concerned. But I think that does run into problems with asynchronicity for the size of the asset class that we're looking at. We will also, as I said, so the mean variance utility approach is somewhat restrictive, ignores skewness and heavy tails. So we will step forward to the constant relative risk aversion, so this class of utility functions determined by the parameter gamma, which measures the risk aversion, and there's a wide range of views on what that gamma parameter should be. So this strand of methods avoids explicitly parameterizing the joint asset return distribution, and then tries to find solutions based on some conditional expectations. When we add covariance into the situation, there's also been a very big literature, and this is just a selection of the contributions. So of course, Michael Brandt's work is sort of seminal in introducing non-parametrics and covariates into this portfolio choice problem. Sahali and Brand extend this to allow for multiple covariates in a direction along which we will also travel, in that they use index models to avoid the cursive dimensionality. There are a large number of other contributions, using sort of linear policy functions, lasso model selection, and so on, in the last 10 years. So let me just say, so this is a rough outline of what's left. So our starting point is going to be the following. So we suppose that the investor is seeking to maximize the following expected utility function by choosing weights, Wi, on each of the assets. And we allow the weights to depend upon the covariance X, the characteristics X across sectionally varying variables, and the time varying variable Z, subject to the unit investment constraint. So we will want to do this in a non-parametric way. So the ideal solution here would not specify any further restrictions on these weights, just allow them to be general measurable functions of these observed random variables. And in that case, you can derive under some conditions a solution to this problem, which will be a vector of functions mapping P plus K into Rn, okay? So in principle, you can implement this and estimate this non-parametrically as a generalization of what Michael Brand started with. The problem here in practice is the cursive dimensionality, which shows up both in terms of the number of conditioning variables that we may seek to use. And in our application, in total, we'll have 37 variables. So this will start to deteriorate the performance, but also in terms of when you have large cross-section of assets. So we're part of a literature that's trying to proceed by reducing this issue by imposing functional form restrictions. Okay, so some time ago, when I started thinking about some of these problems, I was working on additive non-parametric regression with Enno Mammon and Jens Nielsen. And so one approach to avoiding the cursive dimensionality in the covariates is to use additive models, or additive models with interactions, or some kind of structured models. And so, that's one way of proceeding, which is to specify that we search only over a set of functions that are additively separable in individual components. Okay, so that we can break the X and the Z into the individual components, all 37 of them, and then each of these portfolio weights is a sum of functions of a single variable. Okay, and so I was working on kernel methods at the time, and which has some advantages in the sense that you can obtain, lots of theoretical results for that. But the estimation problem here was really a little bit challenging for both in theory, but also in practice, because you have to solve this nonlinear system of integral equations in large number of functions. Okay, so we just gave up at that point. So then the next step was to sort of actually go in a different direction, was to say, well, we know how to solve the one-dimensional problem. The one-dimensional problem's been solved by Michael Brand. So let's just go ahead and solve all of the one-dimensional subproblems and then just model average them. Okay, so that's what we did in this paper in 2016. So we basically do all of this, the one-dimensional problems, and then we just average the weights to get, to take account of all of the covariate information. And we called that model averaging marginal regression, or MAMR for short. So in that setting, we allowed for, multiple time-varying stationary conditional variables. Later work, we extended this to allow for the ultra-large case, so where the number of variables is sort of exponential in the data size, the sample size, okay? And we called that big MAMR, okay? And that was the extension. So that's an approach to dealing with a large number of covariates, where you can break it down into one-dimensional problems and solve that. Okay, so now, so that's where we started. So now we decided to go back to the work with Greg and Matthias on these characteristic-based factor models for returns, as they're more sort of embedded in the finance theory. So this class of models, the characteristic factor model, is given here. I'm slightly changing the notation locally. So this is returns, so an individual return, no time to variation here. And then these are the loading functions. So this was the model that we considered in these two papers, where we have univariate functions, non-parametric functions, just actioning on a single covariate at a time. And then the factor returns are unobserved common sources of risk in asset returns. And we have a sort of a simplifying assumption on the errors here, the idiosyncratic returns. So this semi-parametric model, so we worked out how to estimate this and related it to the Fama-French sort of characteristic named models, the Fama-French portfolios and so on. So for this model, we can calculate conditional means and conditional variances, and we could do sort of mean variance, conditional mean variance portfolio analysis through that route. The estimation strategy here was based on the first moment only, which separated it from the usual factor analysis, statistical factor analysis, where you work with covariance matrices. So just like the observable Fama-French factors, we're able to estimate everything off a mean restriction, okay, which is the good news. For kernel estimation, we had an iterative method that was, for given G, we can estimate the factor returns by cross-sectional regression. For given F, we can estimate the components of G by kernel smoothing in a sort of a backfitting type of iteration. And inside that, the identification condition is somewhat simpler than the statistical factor model, but we have mean zero component functions and variance one. And given those restrictions, we can deliver estimation of these unknown components by a relatively computationally tractable sequence of steps, all involving either linear regression or one-dimensional kernel smoothing. So we established consistency and asymptotic normality of the estimator under quite weak conditions in terms of the idiosyncratic error term. So that was our contribution. So what we're going to build on, though, is the extension of this by Fan, Liao, and Wang, where they nested that model in the with the statistical factor model. Okay, so if beta ij are the sort of usual loadings in a statistical factor model, and our version of this was not to have an error term, so they embed the model to have both a characteristic driven component and a component that's unrelated to the characteristics. So I'll call that FLW. So their estimation method is a sort of a hybrid, I guess, but it seems to lean a lot on second moment restrictions. So they propose to estimate the unknown components of this model by something called projected principal components. So first of all, you project on the x's and you calculate the conditional expectation of y given x. So this involves this loading matrix and the factors. At the individual level, it looks something like this, where this is a sum of additive components, additive functions of a single covariate and the factor returns. And putting it in this matrix format, this is all represented when we bring it to data by an n by n smoother matrix, S. And in particular, they worked with projection smoothers based on sieve estimation. Okay, so they estimate the conditional expectation by a smoother applied to the n by t matrix of returns, or demeaned returns, or excess returns, depending upon the focus. And this first step is important because it will give you uniformly consistent estimates of the conditional expectations. Okay, so although this is an n by t matrix, it is uniformly consistent over n and over t, element by element. Okay, so this is the first step that's called the data projection. And then calculate either the t by t or the n by n covariance matrices from these projected data, and then use the model structure to see that the covariance matrices, the t by t covariance matrix is given by this expression, the n by n covariance matrix is given by this expression. Okay, we still have an identification issue here, but you can see with this normalization, we can peel off the G or the F as eigenvectors of this matrix. Okay, so that's basically what they do and what we're going to do in our application. Okay, so it's a nice paper, and it shows how you can test the hypothesis that these gammas are 0, or test the hypothesis that this is 0. So our purpose is really to use this estimation procedure to deliver a portfolio choice method. So there's been a number of papers, and I'm probably missing quite a few contributions that have extended that paper. So this recent paper in the RFS extends this methodology to the large number of XKs using adaptive group lasso, and and find some important empirical results. So we also use this methodology in a recent paper that's coming out in JBS, where we apply it more to an asset pricing problem, and so we find we also look at sort of testing the model and identifying mispricing functions, which we seem to find in certain blocks of time. Okay, so let me get back to what we're going to do in this paper. So we're going to be we're going to use a two-step approach. So we'll have a general starting point where we have our X's and our Z's, and we're going to do this in two steps. So first of all, we're going to identify factor mimicking portfolios using the cross-sectional information. So these are the QT that depend upon the time invariant characteristics that vary over time. And then we're going to solve the second round problem where we find the weights on those portfolios. Okay, so using the covariate information from Z. Okay, so we will approach this in these two steps. So first we'll explain how we find the QT of X, and we will also explain how, what the dimensionality reducing structures we use. So the factor mimicking portfolios are going to be constructed basically as linear combinations of the G matrix. Okay, so this is going to be for some matrix, J by J matrix gamma, we will construct factor mimicking portfolios, which will be, J by N, sort of J portfolios with weights on each of the individual assets. And the logic of this is if we go back to the d-mean version of the model, we look at the matrix representation here. If we pre-multiply by gamma G, and we will call this our factor mimicking portfolio, we apply this to the first term, and under the restriction that this is the identity or approximately the identity matrix, this will give us gamma times F. And under the statistical assumptions that this averaging, this cross-sectional averaging will shrink this error term so that we have an approximation. This is approximately corresponding weighting of the factors. So these are going to be the factor mimicking sub-portfolios. And the only thing, so we need two things for this. We need to find the G's, and we also need to choose which gammas to use to construct these portfolios. So we're going to do this in a relatively, so we will construct, by construction, we'll go for orthogonal sub-portfolios, and we'll try to spread the portfolio weights as much as possible. So we will define the gammas through a constrained minimization problem, so minimizing the variance of this. That will be our choice for QT. So having got the QT, the next step is really to determine the weights on these portfolios as we go over time. So here we will invoke a single index restriction for each of these conditional expectations. Okay, so the weights assigned to these portfolios will have a vector of single index functions, and we will assume that these are smooth univariate functions, and the theta is a vector of unknown parameters. So we're going to assume common parameters here. We'll have a single index and allow the functions to vary. And we will still have an identification issue, but we could do this a bit more generally if we thought it was worth doing. So then we go back to supposing we have these factor mimicking portfolios, the problem becomes to choose the weighting vector given the information Z. If we impose the modeling restriction, this converts to the problem of choosing the parameters theta and these functions pi subject to these restrictions. Okay, so that's how we will approach it, and then we will have estimation problems at each step. So we will have to estimate these factor mimicking portfolios for each time period, and we will then have to estimate these weights in a sort of Eitz-Hahlia and Brand type of way. Okay, so one of the things that so we have to deal with is that the time series predictors that we have that are commonly used are highly persistent, and in the empirical analysis, three of them, we could not reject the unit root hypothesis over the period that we looked at. And so for that reason, there's some issue about the performance of the estimation. So kernel methods in particular have been argued by Gao and Phillips that not well theoretically designed for this type of setting. So we're going to use orthogonal series as introduced by Dong et al. And in particular, Hermite polynomials, which have a nice properties for unit root type processes. So in particular, we're going to expand each of these index functions in terms of the Hermite basis. okay? And then we will truncate that, and we will convert, therefore, everything will be converted to effectively a parametric, a nonlinear parametric optimization problem. Okay, so you know, we are only doing so this is what we will do. So these parameters phi will be have to be estimated. So there's a little bit of ambiguity in the paper about what we actually do here, but you know, there are different ways of thinking about it. Okay, so but what we should do is to just maximize this empirical optimizer, empirical sample sample problem here. Okay, so given the time series of factor mimicking portfolios, given the basis, the vector of basis functions, Hermite basis functions, we will choose the theta and the phi to maximize this sample objective function using a long time series. Not necessarily the whole time series, we can do subsample, but we will need a relatively large sample size in T, because you know, we start to gobble up parameters with the sieve expansions. Okay, so we'll do this. So we'll have a J by J matrix of phi of parameters and an L by 1 vector of basis functions, and the K by 1 vector of parameters subject to this restriction. Okay, so U is a given nonlinear concave function, and so we will optimize essentially with respect to theta and the elements of this matrix. Okay, and you know, that's very similar to Saheli and Brand, except they're using kernel methods. So here we're using sieve methods, which just instead of localizing in the covariate space, is expanding in a you know, the parametric dimension. So it's a nonlinear optimization with respect to these parameters theta and phi, but with some particular structure that can help you with the optimization. Okay, and so we will measure significance of the predictive factors through a test. So we will do a test of whether some of the thetas are 0 or not, and we will use an objective function-based test, and we will report those results. Okay, so I turn now to the empirical study. So, so we will, as I said, we will use constant relative risk aversion. So we will use this class of utility functions, and we will just run through. We will do it for sort of low, medium, and high risk aversion 2, 5, and 10. In the estimation, we have two non-parametric steps. So we have the step to get the G to get the factor mimicking portfolios. So that is done by an automatic method based on the sample size that's used, which is cross-section. And we will also use an annual window for that. So we'll have 12 monthly observations times the number of assets that we can use for that optimization. And then we use an automatic method for that. So in terms of the second step, where we go with the dynamic predictors, we are using only 4 basis terms for each of the components. All right. So, you know, again, this has not been optimized, and you know, further study could improve the performance. So we will use stock returns listed in the US. So we're looking from 1967 to 2017. There is a correction for delisting stocks that Shaoran has carried out. We will work with a sort of annual kind of horizon. So the characteristics are, you know, fixed for a year ahead, and then they will be updated. We have a total of 33 characteristics. So these are taken from our other paper, which in turn is taken from, I think, one of Andreas's papers. So we use these 33 specific characteristics. And the Z variable are as follows, which are fairly standard time series macro factors. So default spread, term spread, trend, and dividend yield. So in terms of the unit roots, so these three variables, for the series that we looked at, we could not reject unit root hypothesis. The trend variable, the momentum variable, was rejected quite strongly. So we have 37 variables, and the Z's are handled through an index structure. So there's a parameter vector that aggregates the variables here, and then a series of three scalar functions. In terms of the security, in terms of the X's, we again, we are fitting an additive structure to that for each portfolio. Okay, so we will have an additive structure to avoid the curse of dimensionality. Okay, so now here's the bad news. So I think this is where we need to improve the results. So these are the three factor mimicking portfolios, and we have generated a time series of the factor mimicking portfolios of length 600, so 50 years of monthly data. By construction, they are rotated to have mean 0 and variance 1, and these are their sample statistics. This is the correlation with the factor series, factor return series, and you can see the strong diagonal correlation and close to 0 off diagonal correlation. So it seems to sort of mimic the factors as it is advertised. Now here are the tests for the presence of the time series predictors, and here the results are somewhat sensitive, well, very sensitive to the choice of risk aversion parameters. So if we're in the low risk aversion case, we reject the null hypothesis that these predictors have no value. Okay, so quite strongly, except for the momentum factor. Okay, when we go to the higher risk aversion 5 and 10, we cannot reject the hypothesis that they're 0. Okay, so that in the higher risk aversion case, they seem to have less predictive value. In terms of the performance, so this is a summary over the whole 50 years, sort of rolling window, etc. So there's in-sample results, and I think this is sort of, I don't want to defend the indefendable here, but certainly the return looks good, but the standard deviation is obviously completely out of bounds. All right, so there's something wrong, and when you look at it, I mean, it's fairly uniform. In the table we have, in the paper, we have tables that sort of itemize this year by year, and it's certainly the case that some years are extremely large. So there's something that we need to check further there. But it does seem also routinely the standard deviation is a lot high compared to the S&P 500. So I think we do have work to do to improve the performance. As I said, we haven't really optimized this procedure yet. The dynamic weights are, so this is the dynamic weights for the low risk aversion, medium, and high. So these are sort of the time series of weights. And you can see, given the scale here, right, they kind of blow up. These are the weights on the factor mimicking portfolios in the second step. And you can see, especially around about 2000 here. So they're much more variable for the low risk aversion and also for the medium. They're somewhat less variable for the high risk aversion, but they're still too variable. Okay, we have to do something. This is just not really a reasonable outcome. So we need to think of ways to stabilize this. Or we haven't imposed non-negativity or anything else. As you can see, it kind of shoots all over the place. In terms of the out of sample performance, here we use a sort of a dividing sample to do this, and the out of sample performance, again, the mean is great, but the standard deviation seems to be just way too high. So as I said, I don't have an explanation for you. All I can do is apologize that we are presenting something that clearly nobody would buy, but let me just wrap up then. I mean, the procedure itself, we need to seriously rethink. I mean, I get that. I can see that conceptually, I think what we're doing makes reasonable sense. So we have this two-step approach. So first of all, reduce the characteristic, relatively large number of characteristic variables to 3 portfolios, and then solve a relatively small optimization problem to determine the dynamic weights. But it doesn't work very well. So, this is, at least I'm being honest, right? I'm being honest and showing you that, we didn't come here and say this will make you all rich. It will not. And so we have more work to do in terms of tuning the performance. And, so any suggestions that we have would be much appreciated. And yeah, I think I will stop there.
Okay, well, thanks very much, Oliver. We'll turn it straight over to the discussant, Andreas.
Okay, so thanks very much, Andrew, for inviting me to discuss this paper. This is in many ways right up my alley. So it's a paper about optimal portfolio selection in large asset markets. And in some sense, Oliver and Greg Connor have written a lot of the literature that is kind of preceding this, which makes this somewhat of a daunting task. But anyways, we're solving this portfolio choice problem, and then there's kind of this factor timing component layered on at the end. But contrary to brand primarily, they start from the ground up, so with individual assets. So I certainly like this approach a lot, to start from individual assets rather than from some more or less arbitrary pre-grouping of assets. So that's the problem that's being solved, and I'm not going to belabor this since Oliver presented this probably much more elegantly than I ever could, but it's a hard problem, and typically the approaches in the literature are to assume something to solve this, either that really are in low dimensions or that you have quadratic references, and even then it's not necessarily a simple problem. So here we're working with a factor model, and it's a setting where the number of assets is large. And in addition, we observe this kind of X, which is kind of observable firm characteristics, which are informative about factor loadings. And that helps simplify things a great deal. And then there are a bunch of technical conditions, which I'm not going to talk about, and Oliver didn't talk about either. So then you can actually solve a simpler problem that will yield a solution that is approximately equivalent to solving the really complicated high dimensional problem. Okay, so that's ultimately what we're chasing after. There are some questions though that came up when I worked through this, and I want to go through them. So the first question that came across is kind of, what is the role of these sub-portfolios, right? So in projected principal components, the factors directly are readily available. So I've tried to write this in the notation of the paper. G is already being estimated. If you just multiply G with Y and then use the assumptions that are there in the paper, right? So if there's an H, that is, if there's an alpha component, then those two are assumed to be orthogonal, and then there are these error terms for alpha and beta, so this goes away. This converges to something that's approximately the identity, and then you have orthogonality, so what you're left with is essentially the factors. Okay, so in principle, you could think about plugging the factors directly into U. And I can see that kind of this kind of choice of kind of factor portfolio gamma buys you some additional diversification and possibly degrees of freedom. But it's not clear if any of the theoretical results really rely on the choice of gamma. So in other words, you know, does the approximation depend on a particular gamma, such as the one that's chosen in the paper, or could all of this go through possibly with worse performance if I chose gamma to be the identity? So that's something that I think could be made a little more precise in the piece. My second comment is well, rather unsurprisingly, on the empirical success. So it is a little hard to put into context right now. Okay, so Oliver, you know, was very open about this in his presentation. But here are some things that I think would help understand this a little better. So right now, there are many things going on. So, you know, you could try to benchmark this directly against kind of, you know, what if you ran just this portfolio optimization problem using the Fama-Finch 3 or 5 factors as basis assets, and then comparing this to your solution. On top of it is how much does the factor timing help or hurt? I do like I think the series approximation for this factor timing exercise makes a lot of sense. Especially, I mean, you really only need to look up at a plot of the z's to convince yourself that there is an issue with assuming stationarity. And then there's another component that's in principle in there. So we're estimating statistical factors. So typically, we think that statistical factors will do a better job than kind of Fama-Finch factors or something like that. So that could be another source that is potentially helping the performance. So those are kind of some simple steps that I think the authors could look at. More generally, I think you might want to think about what are natural benchmarks for the model that you're computing, and I think you know, starting with the brand is probably not a bad idea. So my third comment is kind of titled "Some clarifications would be helpful." So in the paper, you know, there's somewhat of a disconnect in, you know, we're using a concave utility function, and then at some point it's CRRA, and I can in many ways see how a lot of these things go through with kind of a myopic investor and CRRA utility. And then theorem 3 kind of gives the approximation result for kind of solving the simpler problem, and that being an approximate solution to the really complicated high-dimensional problem. And what was not exactly obvious, in particular in connection to the brand piece, was kind of what's the sense of approximately optimal. So my intuition, and that might very well be off, was that it means something like this, that this kind of estimated expected utility converges to the true expected utility. And then theorem 3 says something about n being large. So that's certainly a condition that I think we need for all this PPCA stuff to go through. Brand's results are all about kind of t being large. Okay, so so that is something that I believe needs a little more clarification when we need which dimension to grow, and kind of what's the sense of the approximation. More generally, I'm wondering kind of which utilities could be approximated. So if we thought of this as being kind of a dynamic program, then you know, you could kind of break so say it was a consumption problem, you could kind of break it down into 2 components, kind of U of C plus the value function of the continuation utility. And then in principle, at least in Brand and Aitzahalia, there are at least hints that this could be generalized for other dynamic problems. And in principle, all you need to do is plug in the value function. So I think it's very natural with CRRA that I think is kind of can be seen very directly, but a more general clarification would help. And then in the paper, there is a kind of some section about kind of demeaning, so time series demeaning the returns, and then projecting the time series demeaned returns on the characteristics, and then kind of applying principal components to the projected demeaned returns. So which is, projected principal components. That part I do not think is necessary. So the demeaning, I think, entered this picture, and you can correct me if I'm wrong, partly because in the kind of general formulation and in Oliver's previous paper and in my own work, we assumed that there was a possible mispricing component, this h of x. And if we're assuming that this is constant over short periods of time, then the demeaning kind of takes out this h of x. So if you then look at the demeaned returns and project them on the characteristics, you have an expression that is only related to risk. And that allows for this separation of alpha and beta. In this setting, I do not think that the meaning is strictly necessary. So implicitly, we're kind of assuming that alpha is equal to 0 and that YT are excess returns. And kind of taking that away could avoid some confusion and complicated notations where I think you actually do not need it. There's also kind of the conceptual issue that if there really was a mispricing component, then probably any risk-averse investor anyways would want to invest in that portfolio because the risk is kind of disappearing in the limit and you're still getting a positive return. So I would suggest just to get rid of this if my conjecture that it's not needed is actually true. There is the ever nagging question on how to choose the number of factors, which I think empirically is not such a big problem. For the theoretical results, I think you do need to say something about it. So typically, we write down some conditions and say, well, we can recover the correct number and then kind of work with the correct number from then onwards. And then kind of everything goes through. And presumably the same thing can be done here. At the current state, it's just not mentioned at all, okay? So since I'm more or less out of time, and I promised Andrew to be on time, I'm going to stop here. I think this is a great paper because it does start from the ground up, like any investor would do, and it can ultimately push us to the problem or to the solution of the problem that we really want to get to. I think there are some things that can be cleaned up, and I'm looking forward to the next version.
All right, thanks very much, Andy. Well, Oliver, plenty of things to respond to if you'd like to have a moment now to do that.
Okay, well, first of all, so thanks very much, Andreas, for doing such a great discussion. And I know the paper's hard to read, and you uncovered all of the holes in what we've done so far. So I liked your comments, and I think I have nothing. I do not disagree with any of your comments. So I think it's we have to follow through with the work to look at proper benchmarking and comparison, and this theorem 3 result. Yeah, we need to provide some argument about that, or it would be nice if we can. And I don't know whether it does generalize much beyond the original setting. And thanks about the demeaning. I think, yeah, we obviously need to relax that, and we don't need to include it. Number of factors, again, in principle, we could do that purely through sort of numerical reusing of the data, but we may be reusing the data for tuning all kinds of things, and it starts to get a little bit out of hand. So perhaps some sort of model selection tool might be a way forward on that front, as well as on the choice of the number of basis terms in the sieve. But these, and more experience with using it and getting it to deliver good results before we. So it's a search across the large parameter space, which is so far we haven't come up with satisfactory results. So thank you very much for your kind and gentle words.
All right, very good. Andreas, if you wouldn't mind ceasing to share your screen, then I can.
Yes.
I think given we're so close to the 1 hour mark, maybe it makes sense to move to the Hangout session for Q&A and to end the formal seminar here. So before we go, normally this is where I'd say, stick around 2 weeks' time, we'll have the next SoFiE speaker. So I don't have anything like that to say today. I do have two things to say. The one is next week is, as I mentioned at the beginning, the annual meeting of the Society for Financial Econometrics. So I hope to see you all there virtually. And then a year from now, the annual meeting will be at the University of Cambridge, and I very much hope it's going to be in person. So I hope to see you all in person at the 2022 SoFiE annual conference. Okay, we'll end it all there.